All right, so let's talk briefly about the lab, okay? So everything, it should be fairly straightforward. Some of you were asking kind of about that terminology on that last page where it said, like, it was like the second harmonic, I think that's what it called for. So when you talk about harmonics of vibrating strings, the first harmonic is going to be the simplest one, where that wavelength is just like, it's like half the wavelength. Okay, you have two nodes and you have one antinode. So the second one is basically where you're just going to have one wavelength within that system. Okay, so that's, you just have to know the terminology. Okay, so fundamental and the second harmonic from there. Anybody want me to go over anything? We're good?
The back page.
Yeah, that's what we're talking about.
What about the back page?
A, B, or C. There's just a lot of confusion.
Oh, this one.
Well,
I didn't know how to do it.
Which part?
I drew a bunch of dots.
That's when the strings
take this to that for a second.
Sorry.
Oh, yeah.
Because in this method, in the actual method.
Okay, Eric, are you talking, which, like, what do you want on that, like,
Okay. No, I don't really want to get through. Says mark and label the points at the greatest average vertical speed. So we draw the second harmonic, and then from there we just.
yeah.
You just draw the second harmonic.
So if this is this wave, okay,
Yeah.
your nodes don't move at all. So which part is gonna have the greatest average speed? Your nodes or your antinodes?
Dude, I'm tired.
He is very
I'm
much
just
the
gonna
type.
say nodes. And
Wait, in spring, where does it happen?
It just
it's an antenna. It's usually there. We go.
On a guitar. When you play it, then that's the second harmonic.
Why are we laughing?
Are we good?
Yeah, we're good. We're good.
I have no
All right,
idea why
so
we're
get
laughing.
that handed in.
How do you want it?
So here's what I want. I want the front page, okay? If you've answered that free response stuff on the second on like on a separate sheet of paper, staple that, and then the last page is going to be the graph.
You trap someone in your pencil pouch.
She doesn't go with them.
She's no longer friends.
Make sure that you hit
I need to take them.
My old percussion.
Remove toxins in general from the movie.
Yeah.
Ingesting toxins.
Hello.
You can't tell me not to ingest toxins.
Yes, I can, but it doesn't mean you have to.
I desire the substance known
Sorry, it's not a substance.
Oh yes, we have.
No substance abuse.
Maybe.
I require drink.
What we have to do is draw a gate diagram.
This is what you catalog.
I'm just going with
Laser block.
I need to like a domestic version of my own phone.
Yes. This is thunderstorm.
Okay. You can look at my site. You can look at my
What?
You can look at my wish list later.
Catalog.
Yep.
going with the big red marker.
A wave ray and
So it's 7 plus 7
photon.
Okay, so, Brian, is that camera still going?
Yes.
Yes,
Okay.
it is.
All right. So if you look at the history of science, one of the big debates was what is the nature of light, okay? And so up until Einstein came along, you basically had two competing different ideas. One is that it was a wave, okay? So like imagine like, they kind of imagine like you have a light bulb or a candle, okay? And just like if you would drop like a rock into a body of water, the wave would emanate out from that point. And so in that regard, if you look at light emanating from the candle, so let's say we darken the room, kind of a weird thing. Oh, no, that's NHS. And we have one candle, okay, in the middle of the room. Don't tell me that's weird. And then you would imagine that that light is acting like dropping a rock into a body of water, where that energy is going to emanate out in all directions from that candle. So in that regard, you say, okay, hey, that makes sense that it's like a wave. But here's the problem, is that when you get into optics, and that's going to be the next big units after this. By the way, your next kind of big test is going to be on Friday, okay? In case you haven't begun to pay attention to what's on it, okay? Waves test is going to be on Friday. Is that you can when we talk about light with optics, so let's say, for example, you can model your eyeball as like a lens, and we draw this light coming in, and it's going to hit this lens, and it's going to cross, and the light's going to hit here, and then it's going to cross, okay? And so your image gets inverted, and you can talk about mirrors and things like that, and you can trace them out as rays. So in some ways, you can treat light as the idea of like a wave. In other ways, you treat it as like this stream of particles that are just going in a straight line, boom, and hit something, and it bounces back. And even if you look at the idea of like a mirror, we're going to spend a lot of time talking about mirrors, where light comes in, it hits the mirror, and then it bounces off. So in that regard, you treat it as a ray, because it's going to come in, it's going to hit, and then it's going to bounce off. So that was, I mean, Newton got involved in this, Huygens got involved in this. If you want an interesting, somewhat, you'd have to be a science geek to do this, but if you're ever tasked with like a research paper in college, do a research paper on the history of light and the arguments in terms of who substantiated it, what was the arguments for it. You know, Newton was able to take white light and run it through a prism and separate it out into its colors. Well, how do you explain a rainbow? You know, things like that, because it's an interesting topic. So here's the big thing. And then you get kind of a combination of both, which is this photon, where it's a wave-particle duality, where it is basically, it's a bundle of energy, which is what we call a photon, but it travels as a wave. So the irony of it is that what we actually settled on was a combination of the two. It's not a pure ray and it's not a pure wave, but it's a bundle that acts as like this tiny, 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 tiny little marble, like a bundle of energy that travels as a wave, but it also travels in a straight line. It gets weird until you actually see the images, and then it kind of makes sense.
I've seen some images.
So when you get into the terminology with light, there's two kind of big things that you need. One is diffraction, okay? And that is, and this is where we treat it as a wave. That's round. I have completely screwed that up.
Writing is difficult.
Let's just start over. Okay. So when you get these two terms and index of refraction and things like that, was a lot of spending a lot of time talking about today. So here's kind of the one way that you can visualize this idea of diffraction. So if you imagine like you have an ocean wave coming in, okay, and you have a concrete barrier here, okay, and when that wave comes in, most of that energy is going to be stopped because of the barrier. But what's going to happen then is that some of that energy is going to come through, but then as it goes through, it spreads out again. Okay? So you take that energy and that energy spreads out. So this is one of the big arguments for the idea of light acting as a wave. So one of the things you can do to show this, and it takes a little bit of technique, if you take your thumb and your index finger and you put them really, really close together and you stare at a light, if you get them really close and they don't touch, you'll actually see that like that it closes the gap. Okay? So what's happening there is that light is going through this diffraction because your fingers are acting like the barrier to the wave. And so when you hold it up like that, and then when you get it really, really close, what's happening is that that energy is coming through, and then as it goes through and it hits that point, then it spreads back out again. So that's why it appears to, like almost merge together before your fingers actually touch because of this refraction. So that was one of the arguments that are going, look, if light was a ray, then it wouldn't spread out. It would be like shooting marbles at this barrier, and if you shot marbles through the barrier, okay, and you were treating them as rays, then the only particles you would have coming through would be straight across like this. You wouldn't have this energy spreading out like this. Now, in contrast to that, you can have refraction, okay? And this is like the bending of light. So, and I'll show you this in just a second. So if light didn't have the capacity to be bent like a ray, then you couldn't have refraction. So come back here. I've got some stuff to show you here. So
Are we doing gravitational lensing? Maybe we should get out
okay, actually, I can show
I think I probably was. I really was.
Vegan chili at like 10:40.
Why?
I'm high on uranium. And she made chili and I'm like, I'm gonna eat some more.
I don't want to. Yeah, just put some.
It was just beans. Just beans.
Yeah, basically just like, it tastes like tomato sauce.
Yeah. So that.
Because it's singular.
Okay.
am a singular.
Tomato chip and beans.
And you also do
It's like baked beans, but they weren't baked. They're kind of
I don't like beans. I like the sweet.
Okay.
So if I know anything about lasers,
Yeah, stay directly. Okay, so okay, so this is kind of the James Bond trick. So I've got this laser coming through here, right? And you don't see it in between, but you see it when it gets to the wall. So why don't you see it in between? Does it just not exist in between?
nothing to reflect off of.
Well, not necessarily to bounce it off of, right? So, but if I give this thing like a spray, okay, then once those particles start to go through, then you can detect where that laser is. So if you have to be in like kind of a James Bond situation, you don't know if they're lasers, then you happen to have like an aerosol can, give that a spray.
Just in your pocket.
I'm just saying, hey.
My travel size aerosol can.
Yeah.
particulate.
So,
He used powdered sugar as well.
Where's your air
Okay.
You could just sneeze.
So,
Just grab the club.
here's what's important, is it, and especially light, if you think about light too much, it just gets really weird, just accept it for what it is. So, these little bundles of energy, these photons, are traveling across. You can't see them until they begin to interact with something, okay? And then it's like they exist, like they're not there, ooh, now they are, okay? So, when you get into this idea of refraction, so what I've got here, this is just a piece of glass. So if I put it in here, and it's at a right angle to the laser, you can't tell any difference. But if I turn it at an angle, now you got to keep your eye on the dot on the wall. So if I,
What?
okay,
That's right.
okay, so I can make that thing nut. Now if I tilt it the other way, then I can make it shift to the other side. Witchcraft, okay? So what's happening, and we'll spend a lot more time talking about this. This is how this is.
Glitch in the matrix.
So here's this light coming in. So in this situation, this will make sense. Imagine that it's like wheels on a car, okay?
Wheels on the car.
And so when it runs into glass, okay, your optimal speed of light, 3.00 times 10 to the 8th meters per second, is in a vacuum. And basically in air, it's the same thing.
Slightly
But
less.
what happens is that when you run into what's called something that's more optically dense, like glass, water, something like that, it slows down. Okay, so this is going to be important. It slows down. So imagine that these are, hold on. Yes, it accelerates. So imagine that you have a set of wheels coming in like this, and these wheels are on dry pavement. So this is like a strip of mud. So when it hits this side of the wheel hits first, okay? So what it does is that it slows this side down, and then when it's traveling through that medium, now it's like this. Now what happens though is that when this side is going to exit first to go back on dry pavement. So this side then is going to catch this first, and then it's going to straighten it back out, and then it's going to be going straight. So what happens is that it hits this, it shifts it, and then it continues straight again. So this is why when I take this lens, right, and I put it at a right angle, nothing happens. So that's like these wheels hitting this grassy, or the mud strip at a right angle. They're both going to slow down at the same time. They're both going to speed up at the same time. But if I do that at an angle, okay, then there's going to be that little bit of a shift because of the fact that I'm making one side slow down, then it's going to speed back up when it goes back up in there. Now, that's another thing. It's like, how does it speed back up? Don't. Just accept it. Okay?
It's not allowed.
It has zero momentum.
Just accept it. Now,
It has zero momentum.
so,
That's not completely true.
It has
what
zero
I'm going
mass.
to do next
Therefore, it has zero
is
momentum.
that
There have been studies
usually when you
like
deal with waves, you deal with two different types of experiments, called a single slit experiment and a double slit experiment.
Yeah, you don't.
So what I've done is I've taken this
There
aluminum
are
foil
one way.
and I'm going to do the single slit first. So what I'm going to do is I'm going to shine this light
They have a little bit.
on here. Okay?
So my vision's blurry, but it's not.
Hold on.
Then it breaks to rotation.
So
Stigmatism.
now, what you've got here is that, notice, and you kind of have to look close, it's tough to see back there. But what you have is a bright spot in the middle, okay? Then on either side of that, then you've got like a dark region, and then you've got another bright region, and then a dark region and a bright region. So now, somebody go up and completely turn even off those front lights. Okay. So now that's easier to see. So what you have, and this is the terminology, what you have is what's called a central maximum. So what's happening here, where that bright area is in the middle, that's where most of that energy is being focused. So this is what we talked about with waves, being able to cancel each other out or reinforce each other. So what's happening, because it's a single slit, you have a certain number of those photons that are going through and hitting here. So what's creating the dark bands on each side is that then you have these waves canceling each other out. So this is justification for the idea that light is traveling as a wave. Because if it was just a ray, the only thing you would have is a single bright maximum in the middle. Okay, that's it. That's the only thing you would see. But because of the fact that you get these alternating bands of dark and light, and notice that it becomes less and less intense the farther out you go, because that light is spreading out as it goes. So this is why you have that central maximum that's at the brightest, but then you have alternating areas. So you have areas where they cancel each other out, where you have no photons hitting, but then you also have other bright areas on either side where they're reinforcing each other. So, and then you have something in between. So you have where they cancel out, and then where they reinforce each other. Now, that's if it's a single slit experiment. So now I'm going to do a double one. So keep in mind what that one looks like, okay? So then if you go to a double, and all I did was I took a razor blade, and I made two cuts very, very close together. Okay. Now, if you look at this one, it's the same type of deal, but with this one, the bands are very, 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 very close together. So you still have alternating light and dark bands, but when you have a double slit experiment, these are very, very, very close together. Because what's happening is that you have two wave fronts that are coming across each other. If it's a single slit, you just have one wave that's spreading out and basically interfering with itself. You'll see this better in a video in just a second. But when you have two of them, this is why you have these bands that are very, very, very close together. Because you have two waves that are coming through, and as they come through, then that's what creates those dark and light bands that are very close together. So you have a cancellation, and then you have a maximum where they're reinforcing each other and making it very, very bright. Now, you're gonna run into a formula. So when you talk about double slit experiments, there's certain dimensions that you want. One dimension that you want is the distance from the screen from where it's being projected out to where it's being received. Okay? So this is going to be one dimension. The other dimension is going to be how far apart your maximums are. Okay? That's going to be another dimension. And then you're also going to worry about how far apart the slits are in the opening. Okay? So those are going to be the three dimensions that you're going to have to keep track of. Now, this takes a little bit of a leap of faith. So I'm going to go turn the front set of lights back on. So I'm going to wing this drawing, so stay with me here. So here's the opening, okay? And so you get these waves coming through, right? And here's the string. So this is actually, even though it's acting as a wave, we actually draw it as a ray. So what happens is that as this one comes through, okay, so this is going to travel this distance. And then this one is going to travel this distance. So what you'll see is that these gaps have to be like a wavelength apart, because that's the only way that you can get like a relative maximum. So even over here, when this comes here, and this one's going to come over here like this, yes?
Did you have any more moments?
I did. Is anybody here taking this class for college credit? Ryan, you are.
Yeah.
Does anybody else have their packet for, or is going to take it for college credit? Was Ryan the only one?
Well, I turned mine in last Friday.
Oh, you already turned yours in.
I think I got a couple earlier.
Oh, you already got
Yeah.
some earlier.
They
Okay,
came
all
in
right.
with other classes.
Okay, all right.
It's not as big as a disappointment you thought.
Huh?
We're not as big as a disappointment as you thought.
Okay, good. I'm going. Seriously? Okay. So, what's going to happen is that this distance that these are going to travel have to be off by a wavelength. So you've got one wavelength here, and then this distance here is going to be off by another wavelength, because that's the only way they can meet, like crest to crest, and get a bright spot. So this is going to be, once we get into the math on this, these travel as multiples differences of the wavelength of light. Got that? Okay.
No.
All right.
That's
So
the way.
turn this off.
Basically.
Now, go turn these lights back on.
Okay. So, there'll be a wavelength apart?
Yep.
Okay.
All right. So what I'm going to do is that I've got corn oil. I'm going to pour this in here. Okay. So then I'm going to take yonder test tube and put that in there, right? And it kind of looks a little bit, you know, kind of off-center, a little bit weird, okay? Because what's happening is that light, because of the index of refraction, is different. So the light is traveling at a different speed, and if you look at, like, let's say for example, I hold this up and I'm gonna see Noah on the other side. Okay? So if you look at the path of the light, that path has to bounce off of Noah, go through the glass, go through the oil, go through the Pyrex, through the air inside of it, through the Pyrex on the other side, through the oil, through the Pyrex on the other side, and then to my eye. Okay, so it's actually a fairly complicated path. Now, if I take this out, oh, it's just from Noah right to my eye, and there's nothing in between. So what I'm going to begin to do is I'm going to begin to pour oil into the Pyrex tube. So Liza, I need you to hold that, dear. Okay, got it? Okay, so keep an eye on the Pyrex tube. Okay, so we're good?
That's witchery.
What?
Dark magic.
I now see your arm instead of your. I now see your
So-
instead of your arm.
Whoa.
This is why I'm banning physics.
Okay?
This is dark
Okay?
magic.
It's dark magic.
Oh, they have similar. They have a
Burn the
similar.
witches.
Index
that-
of, yeah. So the index of refraction of the Pyrex and the oil
It's near.
is the same.
Well, or near identical.
Just,
Okay. Okay, I'll stop.
so when that light travels through, when you alleviate that air, which has a vastly different index of refraction, then it appears to disappear, because now that light can't tell any difference, because those index of refractions are very, very close to each other. So, but if I take this and I pour it back out, okay, let's go back. So now,
That's so,
You cut off
that's
the
so
bottom of the
weird.
I cut off the bottom,
You
okay?
made a shorter test tube that's magically floating
Yeah,
down.
but yet it's like it's hitting the solid bottom, but yet it's only like halfway down. It really is.
And I think
Dark
that's illegal.
magic.
What happens if you look at it from like underneath?
Well, then it looks about here.
Oh, that's weird.
Wait, I want to see.
It looks like a pasta noodle.
Looks like what?
Like those noodles that
I
like.
can't.
Oh, yeah.
I know, that's weird.
It's not even chemistry.
Yes.
Oh.
It looks like. Oh my god.
I know how.
It looks like one of those. What are they called?
Cover yourself in those human.
Those
Okay.
noodles.
So if I
Back?
cover
Got
myself
it? Good?
in air.
Back we go.
Okay. Wow.
Bruh.
It recognizes faces.
I know it does.
I just wanted to flex my underneath.
Ah,
Oh, so that's what you
We're talking about pasta, and suddenly I pull out a
Like I thought it was like that, but I wasn't sure.
wow.
I like how we're calling them pasta noodles now. They're no longer just pasta or noodles. They're pasta noodles.
Well, I mean, you have to specify what's wrong with it.
True. Or rice noodles. Fox is sad. Why is he sad? Or is he is also content. He has a tragic backstory that's untold. Maybe you can find his way.
It probably explains. Is it pasta or pasta?
And he's in some mystical forest. Maybe his best friend sits next to him. I could be the Marcos. I don't know. I like making stories about random things.
Okay, what is that here?
Oh, we
Planck's
did this
constant.
in chemistry.
Energy equals.
Well,
I
I don't have Planck's constant, I don't remember it anymore. Energy.
Yeah, energy equals frequency times.
Okay. So there's two ways that you can, depending upon which book that you look at, there's two ways that you can express this energy of a single photon. One is that it's E equals HF, okay, and no matter what, that H is Planck's constant. It's just a really, really small number, 6.36 times 10 to the negative 34th joule seconds. Don't worry about it for now, it's just a number, okay? But it's a really, really small number. So what that means is that each energy, for each photon, carries a small, very, very, very small amount of energy. So, but here's what's important, is that energy is directly proportional to frequency, okay? So as the frequency, and this is what I tried to show you all when I was like shaking the spring, okay? So as I made it a higher and higher and higher frequency, what happened to the wavelength? It got shorter and shorter and shorter, right? So as the frequency goes up, the energy goes up. But that's caused by a decrease in the wavelength. Now, sometimes you see this written as E equals h nu. This is how I learned it. It wasn't frequency, it was the Greek letter nu. So if you solve for nu, you have E over h. So in the people that had studied quantum mechanics, which were the nerds, I'm just admitting this before I tell this joke, okay? So don't think, oh, Burkamp, you're not cool. I know this, okay? Let's get this straight right now.
But Burkamp, we're not cool.
But if you go to someone who understands this equation, you go, hey, what's new? And they go, E over h. Everybody gets that.
I'm gonna start using that. I feel like I'd be punched if I said that.
I'm just telling you. Now, if people haven't studied Planck's constant in this
They're gonna look at
equation,
you
they're
like you're a weirdo.
you're an idiot. Okay? So choose wisely your audience. So everyone in here, you can say, sup, what's new? E over h. Okay. Because it doesn't work with frequency. It only works with the other Greek letter nu. So that's why I'm, kind of partial.
So wait, was that how you greeted each other in physics then?
That's the official greeting. No, that's the official greeting of
Of nerds.
physicists.
Okay. Now, here's what's going to be important, okay?